Hello, my name is Pedro Alves. I'm a PhD student at University of Campinas in Brazil, and currently I'm a guest at the Aarhus University in Denmark. I did this work with Jheyne Ortiz and Diego Aranha. Let's first do a very quick introduction. Well, it's increasingly common nowadays, the data collection from users. Uh, it happens all the time through our smartphones, computers, browsers, smart devices on our houses, even through street cameras. But is it always a bad thing? Not necessarily. For instance, when we think about security, we may need to find persons of interest for different reasons. About health, we may want to combine data about treatment of patients in different places of the world in different times, and create new treatments, or maybe select the best treatment for a particular person. And of course, traffic data. So if you're going to the work, you may want to have which one is the best route for that, and so on. But the problem is that without sufficient protections, data may leak, and the users may be harmed by this leakage. The problem we are discussing here is about plain texts. So this is a plain text. It's a completely vulnerable piece of information. Anyone with possess of it can do whatever they want to. What we do to handle that is to build layers upon the plain text that adds different levels of security. So for instance, if you want to send it from point A to point B, you can add a transport layer such as TLS. If you want to store it somewhere safely, you can add a storage layer using AES. The problem appears when you need to do some computation with this plain text. With only these two layers, you can do that, so you need to remove these layers, the plain text becomes vulnerable again, so you can do the intended computation. What we would like to do is to insert a new layer under the storage layer that enables someone to do computation without revealing the plain text itself. For that, homomorphic encryption schemes are natural candidates. They allow the evaluation of ciphertext without the knowledge of any of its keys. So today there are some standardization efforts. One of those I can mention is a open consortium with members from the industry, government, and academy. And BFV is one of the main schemes considered by this consortium. However, there are still performance issues to be overcome before we can have a FHE scheme applied to real-world applications. In that context, our work targets the development of implementation techniques to improve the performance of a class of FHE schemes with the ring learning with errors as the underlying mathematical problem. And the chosen architecture for that is CUDA. The reason for that is its considerable power processing powers for data problems. So now I will give a little more formal definition of what a homomorphic encryption scheme is. So a pair of functions of encryption and decryption forms a homomorphic encryption scheme if there is some operation that, when applied on ciphertext, results on another ciphertext equivalent to another operator applied on the plain text. So, for instance, in the Polynomial proposal, when we compute a multiplication of ciphertexts, we have a result equivalent to the addition of the related plain texts. So now I will describe the BFV. The BPV is a scheme proposed by Fan and Vercauteren in 2012. It's based on Bracker's scheme. It is a RLWE scheme, so it's post-quantum secure, what means that there's no known attack based on quantum computers that can break it in polynomial time. The basic arithmetic construction relevant to BFV is the definition of RP. The finite field RP is defined field of polynomials such that each coefficient lies in ZP, and the degree of all these polynomials is up to n minus 1. That's because the field is defined using the 2NF cyclotomic polynomial. The main parameters relevant to this scheme, other than n itself, is t, which defines rt, the plaintext domain, and q, which defines rq, the ciphertext domain. So plaintext coefficients lie in zt, and ciphertext coefficients lie in zq, and q is much bigger than t. Assuming that we have a set of keys formed by a secret key sk, a public key pk used to encrypt data, and a evaluation key or relinearization key evk. I will now present some of the relevant primitives of BFV for this presentation. The two first are encryption and decryption. During encryption, we sample 3 elements, U uniformly from R3, and 2 others, E0 and E1, from a distribution key known as error distribution. Usually in practice, the discrete Gaussian is used as key. And the output, as you can see, is a pair of polynomials, which the first one stores the message itself, m, multiplied by the rounding of a division of q by t. And the second one stores the other part of the public key and is needed to decryption. So the ciphertext of BFV is composed by 2 polynomials in RQ. The decryption uses these 2 parts to recover m, and because we multiplied m by that rounding, we have to undo that here. So we multiply by t over q and do another rounding. Addition is quite straightforward. It's just element-wise addition. The multiplication is a bit more complicated. You first need to compute 3 elements, C0, C1, and C2, which are the multiplication of this ciphertext composed by 2 parts. So now we have 3 parts. To return to the original representation of ciphertext with 2 parts, we need another method that I won't present in this presentation, called relinearization, which receives these 3 parts and the EVK and returns our ciphertext with the original representation with 2 parts. Here, something that is important to notice is that both in decryption and multiplication, we need to execute multiplications by t over q, which is a real number. This is not an integer, and followed by a rounding to the nearest integer. I believe that a brief overview of some characteristics of the processing architecture is necessary for the full understanding of our methods. Our target for this work is GPU processing through the CUDA architecture. CUDA processing is thread group oriented. the hardware splits threads in groups called warps and process these warps just as a vector processor does. However, the GPU has different memory spaces that we need to consider when we are designing a algorithm to work well on GPUs. The three first memory spaces that I will mention here is the global memory, shared memory, and the local memory. The global memory is the memory that is the only memory between these three that communicates with the main memory of the machine. So when you want to compute something on CUDA, you need to first copy data from the main machine memory to the global memory. The shared memory is a space shared by threads in a block. So CUDA divides threads both in warps and in blocks. There are blocks of threads, and each block shares a piece of memory called shared memory. Shared memory is much smaller than the global memory, but is also faster. And there is the local memory, which is the space exclusive to a single thread. So this is the fastest one, and of course the smallest one. Also, there is the constant memory that is important to mention here. The constant memory, as the name suggests, is used for storing data that will not change. It's cached. So a problem of implementing BFV or RLWE schemes on CUDA is that there's no native support to multi-precision arithmetic. So anything bigger than 64 bits will be problematic to implement. A good way to avoid that, commonly used in the literature, is the residue number system, or RNS. The idea to use the RNS is that you have this one polynomial with maybe huge coefficients, with maybe hundreds or thousands of bits, and you replace it by a set with many polynomials with arbitrarily small coefficients. For instance, 64 bits. This is done in practice as the following. So you need a set of coprimes integers, and you can represent a polynomial p, for instance, in the RNS domain by reducing p by each one of the elements of this set. So you end up with this set of residues of p. Inside the RNS domain, we can compute additions, multiplications, and modular reductions by a cyclotomic polynomial, three very important operations to implement BFV. However, integer modular reduction is not supported. You can't compute a reduction by anything else than the related coprime for that residue. You can't execute no integer divisions, and you can't execute roundings. So as I mentioned, the BFV needs these three operations to implement decryption and homomorphic multiplication, and this is a problem if we want to use the RNS. What we do in this work, we follow Halev et al. variant of BFV that replaces such operations by something else supported by RNS domain. All right. So one of the main challenges of working with RLWE-based schemes is how to implement the polynomial multiplication. It's not a trivial operation. A naive algorithm may reach quadratic complexity, and it is used everywhere. So we need something efficient to implement it. Usually, the literature describes techniques involving DFT-based transforms to reduce such complexity. That's because inside the transform domain, the cost of polynomial multiplication becomes linear. The problem with DFT, which is the original algorithm, is that even though the polynomial multiplication cost becomes linear, the cost to apply the DFT itself is quadratic. So there are some variants that fits better the problem. Each variant is defined on a different field. For that, we use a value called omega n, which is a primitive NF root of unity. In the case of the fast Fourier transform, which is one of the most popular variants of DFT, omega n is defined as a complex element. There is also the number theoretic transform, very popular among RLW schemes implementation, which is defined over GFP, where P is a prime. And there is also the discrete Galois transform, which defines omega n as an element of GFP square. Our work follows the proposal of Badawi et al. And applies the DGT. Elements of GFP square can be represented as a pair formed by two elements of GFP. These elements are also known as Gaussian integers. Their arithmetic is quite similar to the complex arithmetic. And there are some very convenient properties for us. For instance, the DGT has natively something called negacyclic convolution. This property offers a free reduction after each polynomial multiplication by a cyclotomic polynomial. And as I said, RLWE-based schemes are defined on a cyclotomic polynomial field. And also the DGT to construct GFP square needs to fold the input polynomial, which halves its degree. This is a very, very important property of DGT because that also halves the quantity of roots used in the transform. It saves memory transfers. This is what turns DGT into a more interesting option for CUDA, which is a memory-constrained architecture. The problem with available formulations of the DGT is that there is a requirement for synchronization in different parts of the algorithm. This is not trivial with CUDA since, as I said, threads are split in thread blocks, and the biggest mechanism we have in CUDA to synchronize group of threads targets these thread blocks. A thread block is limited to 1024 CUDA threads, so this impacts strongly the scalability of such implementation. We also could achieve the synchronization using successive CUDA kernel calls. So for instance, you call a CUDA kernel, do the operations until the synchronization is needed, then you end this CUDA kernel synchronizing forcing synchronization between all threads, and call another kernel to continue work, to resume work. The problem with this is the considerable overhead of calling so many CUDA kernels. I will discuss this a little bit when I present results of our implementation. A different strategy to handle that is our proposal, which we call hierarchical DGT or HDGT. It targets constrained devices. It's based on an original proposal by Bailey and later revisited by Govind Araju et al. These both works targets FFT. So our work had to evolve the technique to support the DGT and arithmetic in GFP square. Right. Now I will give some intuition about how HDGT works. So suppose you have a polynomial a polynomial p with which degree 2n minus 1. The first step is to represent it as a vector. Then you need to fold it such that each element of this new vector will hold element I and element I plus n. For simplicity, I will denote this as tilde A. Then we need to apply something called twisting, which is the multiplication of each element of this vector by a power of a primitive and nth root of I modulo p, where p defines GFP square and is a prime, right? This is the operation responsible to offer the negalocetic convolution in the HDGT. So it's a very, very important step. For simplicity, again, I will denote these elements as tilde b. We will change the vector representation by a matrix representation such that we have a matrix of nr rows and nc columns. The idea is to have nr and nc as near as possible for efficiency. And now we will apply the canonical DGT. First, we apply through the columns, so we get all elements from the first column and send it to the DGT. The same with the second column, and so on until the last column. Then we multiply each element of this matrix by a power of omega n over 2, right? For simplicity, I replace those elements by c. And lastly, we apply the DGT, the canonical DGT, one more time, but down through the rows, just like that. And this is the outcome when we apply the HDGT on PFX. So to evaluate the quality of our methods in practice, we developed a proof of concept implementation, which we call SPOG. It is written in C++ and it targets CUDA. It applies the hierarchical DGT for polynomial multiplication. We designed the implementation as a modular implementation such that the polynomial arithmetic is implemented in the different model than the crypto system. So in this case, the polynomial arithmetic is implemented on a sister library called QPoly. The idea of doing that, it produces a code that can be easily ported to any other scheme based on the RLWE. SPOG uses current to sample the need for polynomials during encryption. Current is a library maintained and offered by NVIDIA. The state machine used by SPOG targets data locality on the GPU memory. So the idea here is that data must be kept on this third stage as much as possible. By doing so, we save time used to compute HDGT and the RNS. The only moment data will need to be taken back from the third stage to the second one is to the computation of division and rounding required by BFV on decryption and homomorphic multiplication. This is implemented on SPOG using high-level et al. Methods. This happens because their methods support the computation on the RNS domain, but not the computation on the DGT domain. Otherwise, we would be able to keep data all the time on the third stage. Now we will compare SPOG with what works in the literature that implements BFV on CUDA. The first one we call BPAVR, which provides benchmarks on a GPU Tesla V100. The problem with this work is that they only provide measurements for the decryption and homomorphic multiplication. So we thought it would be a better comparison if we had more data. For that, we choose also the BVMA work, which also provides measurements for the BFV, but this time running on a Tesla K80. Provides that measurements for all the relevant primitives of BFV, even though it doesn't use a so high-end GPU as the first one. None of these works made their source code public, so for comparison, we had to reproduce the execution environment considering both the hardware and the software, and we did that on Google Cloud virtual machines. And we ran our benchmarks following precisely the versions of the libraries described in both papers and the same parameter size. First, I will provide the times for the comparison between SPOG and the BVMA work. It ran on a Tesla K80 GPU. Homomorphic addition, which is a quite simple operation presented against between 2 and 5 times. Homomorphic multiplication, which is a critical and non-expensive operation, reports speedups between 2 and 3.6, as you can see. Even though optimization of encryption and decryption wasn't our main focus, we could measure considerable gains for encryption and something more modest for decryption. We believe that the gain with homomorphic addition is related mostly to our more efficient state machine with SPOG, since this operation is defined essentially as a coefficient-wise addition. As I said, the BPAVR work is much less descriptive than the BVMA, so we only can compare SPOG with decryption and homomorphic multiplication. Our homomorphic multiplication also presented about 2 times speed up on all configurations, as well for decryption. So a major contribution of this work is the HDGT. So we want to evaluate its quality, and for that we compare it with 2 implementations of the canonical formulation of the DGT, which we call DGT-I and DGT-II. The DGT-I is a has a multi-kernel design in the sense that each synchronization step is done by the ending of the current kernel execution and the call of a new one. So to apply DGT on a polynomial with degree n, we need log n over 2 CUDA kernel calls. DGT-II runs a different design with a single kernel design. So the idea is to use a single CUDA kernel to process a entire polynomial. So the synchronization is limited to the block level, so we can process up to 2048 degree polynomials when folded. When compared with DGT-I, we do this comparison considering 3 cases: the latency needed to compute the transform, the latency needed to compute encryption, and the latency needed to compute the homomorphic multiplication. The only difference between any of these implementations is the use of DGT-I or the HDGT. So when compared to the DGT-I, the HDGT presented 2 times faster latencies to compute the DGT itself and homomorphic multiplication. The comparison with the DGT-II offers different numbers, though we measured slowdowns on most cases on Tesla K80 when the HDGT is used. Some speedups were noticed on the Tesla V100, but not for homomorphic multiplication. This can be explained by the bigger overhead of a HDGT implementation, which uses 4 CUDA kernels to complete the computation, while the DGT-II uses only 1 kernel. Well, that's it. As future work, we mentioned the need for a careful direct comparison between the HDGT, the NTT, and a hierarchical version of the NTT running on GPUs. I think it's quite important to do as a next step. Moreover, we expect the implementation of other RLWE-based schemes using SPOG, as for instance the CKKS. And lastly, we'd like to have some benchmarks of more complex applications, for instance, machine learning algorithms running over SPOG, both on BFV and CKKS implementation. I'd like to thank CNPq, CAPS, and LG for the financial support during this research, and Google for the support in the form of Google Cloud credits. Thank you very much for the patience and interest on our work. Thank you.